Yeah, thank you very much for this kind introduction. Also, thank you very much for having the opportunity to give a talk today. My name is Florian Funke, and I'm from the materials department at BMW, and I'm responsible there for, yeah, I can advance it. Yeah, I'm a materials engineer at BMW. I'm responsible for additive manufacturing and also machine learning and or applying data-driven methods into material qualification. And today I would like to talk about a use case we had together with QCware last year in terms of additive manufacturing. And there we tried to apply a quantum machine learning to predict the mechanical properties of 3D printed aluminum. Okay, let's start with 3D printing and optimization. Why is it a thing, and what's 3D printing anyway? When we talk about metal 3D printing, the most widespread application or the most widespread process is laser powder bed fusion, which basically solidifies metal powders via a laser. You advance a metal powder, you coat a metal powder onto a build plate, then the laser selectively melts the powder and solidifies it, and in the end, after each layer, the build platform is lowered a little bit, and then the process is repeated until the full part is built up. And in this, yeah, and I've got a video for you how it works. So let's start. Yeah, you can see here, this is the powder bed. The laser outlines the cross-section of the parts. And then also this happens here. This is the so-called hatching process, where the entire cross-section gets solidified. Afterwards, the parts are de-powdered. And in the end, you will have a semi-finished part near net shape, and which will have some degree of post-processing in the end, but you have a lot of parts that could be built. You have a lot of design freedom, and it's a really nice process in order to prototype or to do some intricate parts. And as I said, we start from the pre-product, the powder itself. Then we have the AM process in the process chain. Then after that, we have a so-called most of the time an intermediate state, which is the as-built state, which is then most of the times heat treated. We have some surface treatment or also some machining on the parts in order to get it to the perfect size. And then in the end, we have the final state, which we would qualify at my department in order to get the requirements tested on these parts. And as you can see, there are a lot of variables that can be tuned and optimized, and it's quite a challenge to do a global optimization in this process. And for the sake of this argument here, we will focus just on the AM process itself and the resulting material properties after the printing process. And this here, as you can see, or as you have seen, the laser material interaction basically defines how much energy is put into the material, how the material solidifies in the end, and which material properties come out of it. So there's a high dependence on the process parameters which we use as inputs. And this is quite intricate because we have around about 30 parameters to optimize. And this parameter space is really difficult to get a global optimum out of it. That's why we would like to, we try to apply machine learning to it. And for the machine learning, we used from the input parameter side, the laser process parameters like laser power, laser scan speed, the laser focus, scan distance, or the layer thickness of the powder. And with this, we printed with 50 parameter combinations, 148 tensile specimens, and which we generated our materials properties. And target values were the yield strength, ultimate tensile strength, and the elongation at break. For those who are not so familiar with this is basically the points in the stress strain curve when you pull a sample. The yield strength is basically the elastic maximum tension, which is which can be achieved by a sample. The tensile strength is the maximum overall or the maximum plastic deformation of the sample without breaking, and then the elongation at break is basically the elongation of the samples after breaking. And these are mostly, or these are the typical values we would evaluate in terms of getting a first grasp on how a material works or behaves. And that's why we chose these 3 values as our target values. And then with this, we built a machine learning algorithm, in this case a neural network, which is quite dense in terms of the depth we had. We designed it. On the left-hand side, we had our input parameters like the laser power and so on I showed before, and also these asterisk values are dimensionless values, which derives from the actual scalar values we put in. And then we had, for each target value, we set up the exact same network, but for a single output. And as you can see here on the right-hand side, the classical neural network performed quite well, even with these small values or small data sets we applied. And for example, the yield strength and tensile strength were around, had R squared values of 0.77, 0.8, so it was quite good in terms of the model fit. The elongation at break was a little bit more finicky. It's here with 0.74 was the least well predicted target value, but in the end it was also the one which had the most the most variations in terms of their measurements. The only issue is we have always the small data set problem in material science, because every tensile sample has to be fabricated, has to be tested, and has to be evaluated. And that's why sample sizes over 100 or 1000 is rarely common, or at least very, very seldom. So that's why we will always have this small data set problem, which will be the challenge to apply machine learning in the realm of material science. Now you may ask, why quantum? And this is the point. In 2022, we came across a paper which stated that it might be possible to use quantum computing for machine learning models, which might generalize faster than conventional algorithms. And that's why we said, yeah, it would be a good idea to try this out, especially in this with our small data set problem we have right now. And that's why we started a collaboration with QCware last year in order to get or to try it out, basically. In terms of how does machine learning work in the quantum world, basically you have an analogous in the quantum world with these orthogonal neural networks. So on the right-hand side, you have the classical algorithm, basically between two layers, you have your connections. And on the on the left-hand side, the quantum world works basically the same, looks a little bit different, but it's also an orthogonal network with these RBS gates connecting each qubit with another and entangle and intertwines it with each other. And you have basically the same system you work in. What we try to do is then to get our task. First, we want to learn a quantum algorithm, and then we want to do the inference. So with the test set, we split our data set into 2 parts. And then we tried our baseline model again, the classical model, which was trained on a on a classical computer with a classical architecture, and also the testing was done on the classical computer. And so the baseline I showed you before. And on the quantum side, we tried two things. Firstly, we trained our models on a classical computer, but with a quantum simulator. And then the trained models were either also tested on the quantum simulator or tested on quantum hardware, actually. And that's there we use the IBM hardware for that. We used also different algorithms. We started with the quantum hybrid multilayer perceptrons, but we also tried quantum compound MLPs, quantum variational MLPs, and also the sequential architectures and more. But for the sake of this presentation, we will keep it, stick to the quantum hybrid MLPs. And there, basically, it was built like this. We had a classical input and output layer, and in between, we had the quantum orthogonal layer. And it depended a little bit on the quantum hardware we used, but for the quantum simulator, we could just use the entire architecture we planned so far. On the quantum hardware, as you will see, we used a little bit smaller algorithms in order to get it running on the actual hardware. And in terms of results, it was quite exciting to do these experiments. Let's start with the quantum simulator. As you can see here, yield strength and tensile strength were also predicted quite well, even better than the classical neural network, which has just the basic architecture I showed you before. It was not too massively different, especially yield strength was quite the same, but tensile strength was a little bit better, and also elongation at break, which was quite surprising that it worked better than the classical analogous, which is quite good. On the other hand, we had a little bit increase in the mean absolute error, but I think it's still quite well behaved. And then the actual hardware results were a little bit, a little bit less in terms of their prediction power, but we also faced a lot of noise, and we had to do a lot of noise reduction and quantum error correction, and these were the results, which were not as good as we had hoped for, but in the end was also quite decent. I think, at least with the challenges we had, and also with the smaller algorithms we had to use. Okay, and that's what I would like to conclude so far. As I've showed you, in material science, we have also these small data set problems, which are definitely a challenge in terms of applying machine learning to optimize technical systems. We had the inclination that maybe quantum machine learning could offer a tool to increase the prediction power for on small data sets. And yeah, we tried a lot of different hybrid networks, and the quantum simulator results just showed, it might be possible to have a benefit, but depending on the algorithm, it was a little bit different in terms of which value was better predicted than the other. But but there was a little bit of hope in terms of getting better results. But the actual hardware results were, in terms of that, a little bit disappointing, but due to high noise and a high error correction necessity. But in terms of what we could do, these are the last two steps. For example, if we take an outlook, what we would like to do in the future, or what would make sense in the future, is firstly enhance the QMLP size, so the quantum layer onto the actual values, for example, up to 16 qubits, in order to have a fair comparison between the algorithms. And also, what would also be interesting to use quantum hardware with all qubit connectivity instead of the next neighbor connectivity we used or we had on the IBM hardware. For example, here the Honeywell H1 and H2 QPUs could be have a all qubit connectivity. And on the other hand, we could also build a full quantum model, as I would say, and this would involve doing the training and the testing on the QPU in order to leverage the full data set into the quantum hardware. Yeah, and that's the outlook for so far. Yeah, thank you very much for your attention, and I'm looking forward to getting your questions.
Any questions?
Thank you very much. I have a question about how the quantum and classical models correlate in terms of the number of trainable parameters, because I mean, what's the difference between them? Is there are they the same in that regard, or?
That's a good question. I would like to forward to Natanj.
Yes, hello. I'm Natanj from QCware. So thank you for the presentation. And I would like to answer your question by mentioning that we had the same models in terms of the size of the layers. Let's say if there was like a 16:8 or 8:4 or any layer size. So it was the same for the classical model and the quantum model. However, when we do the quantum neural network, we are doing an orthogonal neural network, which is why it is different. And imposing that orthogonality constraint brings, it reduces the number of parameters. And that becomes n choose 2 parameters instead of n square parameters. So that is you have less parameters to train and still have let's say a better performance due to the benefits of orthogonality, which is a classically studied thing.
Okay, thanks.